The goal of this project was to run a rover through different types of tracks without hitting walls. The track consisted of straight lines, different types of curves, crossroads, and sections where the width of the track were not even. There was a finish line at the end of the track, and the rover had to stop within 3 inches of the finish line. Also, the motion of the rover had to be controlled wirelessly. The rover had to finish the course within 3 minutes. To accomplish this goal, there were 3 important parts we had to complete: hardware implementation, communications between PIC boards, and software algorithm.
Here's the block diagram that shows the component layout of the project. The right side is the rover, and the left side is the controller, which was built on the breadboard. The hardware parts that make up the project include 3 PIC-18 microprocessors at the brain of the project, 1 for the motor controller and the encoders, 1 for the sensors, and 1 for the remote control of the rover. We also have a motor controller and motors to drive the rover, the encoders to read the speed of the rover, 2 IR sensors on the side, and 1 ultrasonic sensor at the front to detect the walls. We also have a line detector sensor to detect the finish line. There are XB units for wireless communication between the rover and the controller. As you can see, the main communication protocols are I2C and UART. I2C was used between the PICs on the rover, and UART was set up for XB wireless communication and the communication with the motor controller. Here's our assembled rover. On the top, we have our circuit board built here with the PICs and the XB unit. We also have 2 IR sensors on the side, 1 on the left and 1 on the right. At the front, we have the ultrasonic sensor. At the back, we have our line detector sensor. Here's our controller board. Similar to the board on the rover, we assemble our PIC here, and also our XB unit. Each of these components will be implemented and tested separately, and then combined together. The success of these single components will determine the success of the whole project. In our system, we define a universal set of message structure that can be used across the whole system. Each message has 4 bytes. The first byte contains the message tab, and the last byte is a corresponding match of the message tab. We are doing this because we want to ensure that we are receiving the correct message that we are supposed to receive. Each time a message is received, our PIC will match this first byte and the last byte to determine whether to keep the good message or discard the junk ones. The middle 2 bytes contain the data. It could be either sensor data or motor speed data. Now, let's discuss about our implementation of the components. First of all is the motor controller. The motor controller we use here is one of the Cybertooth motor controller series from Linux Motion. The motor controller communicates with the PIC to UART. Each time a message of 2 bytes will be sent by the PIC, 1 byte will contain the speed for the left wheel, while the other byte will contain the speed for the right wheels. To drive the rover straight, user can send the same speed to the left and the right wheels. These rovers can go straight at the maximum speed of about 25 to 26 inches per second. For soft turn of about 30 to 45 degrees, user can make one side spin slower than the others. But for sharp turn, user can make one side spin backward, while the other side spin forward. On the front, right and left motors, we also have 2 encoders attached. These encoders can read the spinning speed in revolution per second of the wheels. The PIC can then read the signal produced by the encoders, catch that frequency, and then convert it to the current speed in inch per second of the rover. Due to friction on the track, the actual speed of the rover is always slower than the desired speed that was sent to it. Therefore, the current speed of the rover measured by the encoders can then be used in the feedback loop to adjust the actual speed of the rover to the desired speed. This helps improve the performance of the rover.
Three types of sensors were used for this project: ultrasonic sensor, IR sensors, and line detecting sensors. Among these sensors, the ultrasonic sensor and IR sensors were range sensors. These sensors were capable of detecting walls in front of the rover, as well as on the left side and right side. Once they detected walls, they returned distances. Checking if these range sensors were working correctly was crucial in this project because it could prevent the rover from hitting the walls. To be able to successfully send sensor data, each sensor value was sent to UART to transmit as a 4-byte message, and these sensor values were received by UART receive on XBee PIC to determine the navigating commands it should send back to the sensor/master PIC. After assembling all the components to test the rover, our group came to realize that the rover could have run in the middle of the course and lower the chance of hitting walls by having longer range IR sensors, since our IR sensors could only detect up to 11.8 inches, and when mounted on the rover, sensors were located about 4.5 inches inside the rover. To improve this limitation, using IR sensors that can detect up to 20 inches is necessary. In addition to these range sensors, we used line sensor. The line sensor was capable of detecting the dark line, which in this project was a finish line. Once the sensor detected the line, it triggered port B external interrupts and informed the XBee PIC by sending a 4-byte message through UART. This process was important in order for the rover to stop at the finish line. A disadvantage of this line detecting sensor was that it sometimes detected black dots on the ground. This problem could be fixed by running the rover on the bright colored ground and having a completely black finish line. This is ultrasonic sensor, IR sensor, line sensor, and line sensor on the rover bottom. To wirelessly communicate between two PICs, successfully implementing UART transmit and receive was necessary. The XBees were able to transmit and receive all the data without losing bytes through UART, and this was verified by displaying received data on XBee Explorer and Logic Analyzer. While setting up XBees for the wireless communication, we realized that it was really important to read and understand the datasheet fully. Before supplying the power, we read the power requirement section that the power required to turn on XBee was 3.3 volts. We supplied the power but never checked how much we were supplying. We spent almost a week trying to figure out why the XBees were not working when UART transmit was correctly implemented. Later on, we found out that we were not supplying 3.3 volts. Fortunately, we were not supplying more than 3.5 volts and XBees did not explode. This incident reminded us how important it is to understand the datasheet fully, as well as checking the amount of voltage we supply to electronic components. This is XBee on XBee PIC, and this is XBee on the rover.
The navigating algorithm is set on the controller PIC. On this PIC, the sensor data are collected. The navigating algorithm will use this data to output appropriate action for the rover. The logic for our navigating algorithm are as follows. At soft turn, or when the rover is too close to a wall on the side, the rover will spin up the wheels on that side to make a soft turn. Soft turn can be detected by the front ultrasonic sensor. For example, at a 90-degree curve, there will be a wall within the threshold of the ultrasonic sensor. In this case, the rover will compare the distance to the left and the right wall to compare the direction to turn. If one side closer than the other, it means the rover will have to make a sharp turn to the opposite direction. Here's the video of our final product after putting all the components together. Our rover can navigate through a track without hitting the wall, and also can stop after passing the finish line.